So thanks everyone for joining us. Today our speaker is going to be Gabriel Samach from MIT. So he's a graduate fellow in the Engineering Quantum Systems group. And previously he had worked with Bill Wooters at Williams College. The reason he's going to talk to us today is about something that's very close to our heart, which is understanding the dynamics within a quantum system. And in particular, he's going to talk about understanding the Lindblad operators of the system. So with that, I'm going to turn it over to Gabriel. Thanks very much.
Hello, everybody. Thank you so much for coming today. Thank you, Joe, again, for the very kind introduction. My name is Gabriel Samach, and today I'm going to be talking about a recent qubit characterization protocol that we've developed, which we call Lindblad Tomography. So to start, I just want to give a huge thank you again to Sohui Tan for reaching out and inviting me to give this talk, and then to Yanina for organizing. And I want to acknowledge from the very beginning that this work was very much a hybrid theory experiment work, where the experiment was carried out at MIT by myself and my colleagues in the Engineering Quantum Systems group. And the theory was developed in large part by Johannes Beauregard, who's a professor at TU Delft, and Matthias Christandl, who's a professor at the University of Copenhagen. Okay, so the motivation for this work is, in some sense, the motivation for a whole lot of work happening in quantum computing right now. So over the past few years, there's been enormous progress to developing quantum computers based on a number of different hardware platforms. However, despite this enormous progress, there are a number of significant bottlenecks that need to be faced on the path towards fault-tolerant, error-corrected quantum computation. And so when I imagine this problem and these series of bottlenecks, the one that comes to my mind most clearly can be maybe best seen in this figure on the right, which I took from this great review article on the subject a couple of years ago. And this is the need for redundancy in the number of physical qubits to logical qubits to develop error correction protocols. So here, each colored symbol corresponds to a physical qubit in a tapestry of the surface code. And here, zooming in, highlighted were all the experimental demonstrations of components of the surface code up until the publication of that review article. So this overhead is daunting from an experimental standpoint, to say the least, but there's hope. So it's recently been shown that tailored quantum error correction protocols can be developed, which drastically reduce the overhead required for error correction by accounting for device-specific error channels. Now, if we want to pursue this path, we require new characterization protocols for really investigating the lost channels in NISQ devices to allow us to design these really tailored low overhead quantum error correction protocols. But these characterization routines are in some sense generally useful for a whole bunch of areas in the field. So for example, we can use them to develop more accurate device simulations. We can use them to detect physical sources of errors in our device, such as crosstalk and really a whole range of things. And so as an experimentalist, I imagine that I have a toolbox of characterization, verification, and validation tools at my disposal that I can draw on to characterize different parts of my device. And this toolbox would include things like standard T1 and T2 measurements. It would include process tomography, randomized benchmarking. And here in this work, we're simply adding a new tool to the toolbox that complements the ones we had before. So this technique, which we call Lindblad tomography, is a novel protocol for reconstructing the dynamic loss channels of multi-qubit devices from an ensemble of time domain measurements. And as I'll go through throughout the rest of the talk, Lindblad tomography consists of both a measurement protocol, so things we do in lab, as well as a series of analysis routines to interpret the results of our data. And in some sense, this slide here stands in as kind of an outline. Over the course of the talk, I'll be going through what this measurement protocol means, and as well as what each of these analysis modules corresponds to. And up front, my sales pitch, when I try to convince people why they might want to use this and why it'd be easy to implement in their lab, is that Lindblad tomography is hardware agnostic. So in this work, I'm going to be talking about superconducting qubits, but you could run it as easily on another platform as well. And in some sense, if you can run a T1 or T2 measurement in your lab, you can run Lindblad tomography. So the overhead required for implementing this technique should be fairly straightforward, given the techniques that experimentalists are already running in their lab. Okay, so to start off, when we think about this toolbox of techniques, what do they all have in common? Well, one way I'd say it is that they're all techniques for characterizing quantum channels. And when I talk about a quantum channel, the kind of cartoon I have in my mind is that we have some set of qubits on the left. Something happens to them, and at some later time, we have a new quantum state. And when we think about all the different things that could happen to our qubits in this evolution, the options are myriad. So we could run in algorithms, we could do something intentional to our qubits, but we can have any number of error sources along the way. So for example, we could have spontaneous emission as our qubits exchange energy with their environment. We could have dephasing, we could have crosstalk between our physical qubits. And as an experimentalist in all sobriety, I acknowledge that we probably have some combination of all of these and more to various degrees. So what we really need right now as we design these quantum computers are techniques for characterizing what happened to our qubits during this evolution. Okay, so let's break down a little bit more what we mean by quantum channels and quantum evolution. So when we talk about quantum evolution, maybe the first thing that should really pop into your head is the Schrödinger equation, which is the backbone of all of quantum mechanics as we know it. And as a quantum computing experimentalist, when I think about the Schrödinger equation, I think about something like a pi pulse. So here we have our qubit state initialized into the 1 state, for instance, and I'm going to coherently rotate it into the 0 state. This process can be well described by the single qubit Schrödinger equation in the sense that it can be described by a single qubit Hamiltonian. So in this case, the dynamical operator is just the poly X matrix. And I'm not going to belabor the Schrödinger equation in a whole lot more detail, except to say that under the single qubit Schrödinger equation, your qubit state will always be confined to the surface of your Bloch sphere. And you're assuming that your qubit is going to be a closed quantum system. So all information that you put into your qubit state stays in the state for all times. Now, again, as an experimentalist, we know that the picture is not so clear. And indeed, there are things that can happen in lab which cannot be well described by the Schrödinger equation, or at least the single qubit Schrödinger equation. So for example, in lab, we might notice T1 relaxation. So here we prepare our qubit in the 1 state, and then over time, our qubit state will asymptotically decay to the 0 state. And this process cannot be described by the single qubit Schrödinger equation because the qubit state is no longer confined to the surface of the Bloch sphere. And this shouldn't be a surprise to us because we know in real physical systems, our qubit is not a closed quantum system. Indeed, there are many degrees of freedom in the environment, and the qubit is going to be exchanging energy with them. So the state will no longer be confined to the surface of the sphere. However, this isn't a problem for modeling the state as long as we add a few more terms to our dynamical equation. So here we can model this by expanding the Schrödinger equation into what's often called the master equation in Lindblad form or the Lindbladian. And here we can now capture T1 relaxation, not by a Hamiltonian, but by a series of so-called jump operators, where the jump operators no longer need to be Hermitian matrices. So here I've written down the jump operator for amplitude damping, and it will come with an associated decay rate. And this is what we think of as the decay rate of the T1 process. So something I like to point out at this point to experimentalists is that, T1 measurements are very standard. They may be the first thing you will run on a qubit when you're vetting it for use in a larger system. But when we take a T1 measurement, in some sense, we're assuming the form of the jump operator, and we're just measuring the decay rate. Whereas Lindblad tomography, as I'll show later on in the talk, is going to directly extract the form of the jump operators and give you some more intuition for actually the structure of these errors that cause your qubit state to decay. Okay, so I like to break it down like this. We can think about different types of quantum channels. corresponding to different parts of our dynamical equation. So for example, if our qubit state is perfectly described by the Schrödinger equation, we call this unitary evolution. So here, information is being conserved inside the quantum system, and this is well described by a Hamiltonian. If we expand this to the master equation, we can now account for these so-called Markovian errors. So here, information is leaking out of the quantum system, and this process is well described by a Lindbladian, by the jump operators and their decay rates. But you'll notice I've left this kind of evocative white space at the right of the slide, and that's because there are processes that can't be captured by either the single qubit Schrödinger equation or the corresponding master equation. And we call these processes non-Markovian errors. So one way to think about these errors, and I'll go into more detail in a few slides, is that in these processes, information is cycling in and out of our system unpredictably. And these, as I say, can no longer be described by a Lindbladian, by the master equation. And in some ways, this is kind of the wild frontiers of errors that might pop up in your processor. So this is all kind of abstract, at least to an experimentalist. So I'm going to kind of drill in and show what this means for the devices that I study in my lab. So in the engineering quantum systems group at MIT, we work primarily with superconducting qubits. And throughout the talk, I'm going to focus on this device that I show in this SEM image on the left. So this is a linear chain of capacitively coupled flux-tunable transmon qubits on a silicon wafer. Throughout this work, I'm going to focus on two of the qubits in this chain, which I'm going to call qubits A and B. And this device is going to be measured in a dilution refrigerator at a base temperature of about 20 millikelvin. So for this device, we can start by writing down the Hamiltonian describing this system. And in the Diffard-Detuned limit, we can write it down as follows. We can write it down as Hamiltonian corresponding to qubit A, Hamiltonian corresponding to qubit B, and an interaction term, which I'm going to call HZZ. I choose this name because in the transmon qubit community, this is what's commonly referred to as the always-on ZZ coupling due to, in this case, the fixed capacitance between our two qubits, which manifests as a shift of the 1-1 state away from its bare frequency. And it gets its name because you can take this Hamiltonian and expand it out in terms of Pauli matrices, and you get one term that corresponds to poly ZZ. So one thing I want to emphasize is that, to first order, qubit coupling can be an extraordinary resource. So this interaction term, a lot of engineering effort is put into designing it well to, for example, harness it to perform high fidelity 2-qubit entangling gates. However, always on coupling can lead to errors. So this resource that gives you entanglement when you want it can also lead to entangling errors, perhaps when you don't want it. And throughout this talk, I'm going to show how Lindblad tomography can help you really diagnose and see these errors more clearly. Throughout the talk, instead of showing you this pretty picture on the left, I'm going to simplify it and show you just this cartoon. So here are our two qubits, A and B. And to give you an idea about what Markovianity means for superconducting qubits, let's consider a thought experiment or a little toy model. So let's imagine that we prepare our two qubits both in the plus superposition state, and we let them evolve naturally over time. So to start, we can write down the 2-qubit density matrix corresponding to this product state of the 2 plus states. And we can ask, okay, what happens if we just do nothing? And by doing nothing, I'm going to refer to this idea as the idling channel for our device, where the idling channel is just a fancy name for doing nothing, for a variable time delay between state preparation and measurement, where the qubits are allowed to evolve freely and interact with each other and with their environment. So in the absence of noise or crosstalk, the idling channel is absolutely equivalent to the identity channel. The qubit state would never change. But we know in our device that such is not the case. And specifically, when we have this always-on coupling between our two qubits, if we allow them to evolve for some amount of time, we may find at a later time that our two qubits have become totally entangled. So we may find that we have a Bell state of our two qubits. But if we were to allow our qubits to continue to evolve undisturbed, so we do nothing again, we may find that the qubits return to their initial state. So if I look at this movie from initial state to entanglement and back, it's pretty easy to see that this is just unitary evolution. We know what the Hamiltonian of the system is, and the two qubits are just evolving according to it. So all information is being conserved inside the quantum system. Now let's play the exact same picture, but now we're going to ignore qubit B and just look at what happened to qubit A. And there are a number of physical reasons why this might happen, why we might be ignoring qubit B. So for example, we might be running just a single qubit algorithm on a large processor and not paying attention to what's happening into the neighboring qubits. Or perhaps qubits A and B are simply far away from each other on their device. So we're not paying close attention to what these two qubits that are spatially separated are doing relative to each other. Okay, so we play the same movie. We have qubit A in its initial state. This is just the single qubit plus state. We do nothing, we apply this idling channel. And now at some later time, we'd find that our qubit is in an incoherent mixture. And this might be alarming in the single qubit picture, but there's nothing particularly mysterious happening. Because we know that meanwhile, in the two qubit picture, our crosstalk has entangled our qubits into, in this example, a Bell state. And when we just look at qubit 1, we're tracing out qubit B. So when you trace out qubit A from the entanglement, you get an incoherent mixture. It looks like you lost all your phase information. And at this point, you might conclude, okay, we have a Markovian error. The information has just leaked out of our system. But if we let our state continue to evolve undisturbed and we do nothing again, we'd find that the state returns to its initial configuration. And this is exactly what I mean by a non-Markovian error. So here we had some phase information stored in our state. It appeared to disappear in time, to be lost to the environment, but then it cycled back in at some later time. So to kind of give you the bullet points of what I mean by non-Markovianity in this talk, is that non-Markovian errors, you can think about them as occurring when your system gets entangled with their environment. This is commonly referred to the environment having a memory or saying that the errors are correlated. And these can be notoriously difficult to error correct on real devices. Another thing worth saying is that in some sense, Markovianity is a matter of perspective. So in the best case, you can control and model the environment. So for example, you can model the degrees of freedom of the other qubit, qubit B, and really see where this error is cycling into before it ultimately comes back. But worst case scenario, you can't control or model the environment. So this exchange of information might be totally unpredictable and really hard to fix in a real processor. And no one knows how to model or correct these non-Markovian errors in general. So when we think about characterization protocols, we really want tools to determine if our devices have these errors and then to hunt down their source if possible, to diagnose them and then maybe in device to suppress them, to make them less prevalent. Okay, so I've talked a lot about Markovianity. What does this have to do with Lindblad tomography and what can it do for us to answer any of these questions? So Lindblad tomography is going to be a technique to extract the Hamiltonian, jump operators, and decay rates, describing both the unitary and Markovian parts of the evolution. And then as for these non-Markovian errors, it's going to give us all the information we need to quantify the degree of non-Markovianity in the channel, and then ultimately help us diagnose its source. So as an experimentalist, when I think about implementing any qubit characterization protocol, I like to have some intuition for how different it is from what I'm already doing in lab. And for Lindblad tomography, I like to tell other experimentalists that it's very much a hybrid of techniques that we're already doing, just putting them together in a way we haven't yet. So the way I like to describe it is that Lindblad tomography is in some sense a hybrid of process tomography, a T1 or T2 measurement, and then classical optimization. So Lindblad tomography is like process tomography in the sense that we're going to cycle over a set of initial qubit states and measurement axes to reconstruct an instantaneous process map. However, it's like a T1 and T2 measurement in the sense that we're going to sweep a quantum channel and watch how information moves between the qubits and their environment in time. And then finally, we're going to use classical optimization to run a classical maximum likelihood estimation which will help us back out the dynamic, Hamiltonian, and Lindblad operators, which best describe the results of our measurements. Okay, so here I've drawn the single qubit measurement protocol corresponding to Lindblad tomography of a single qubit. And I'm going to walk through what each of these blocks corresponds to. So to start, we're going to initialize our qubit as close as possible to its ground state. Then we're going to apply one of 6 single qubit gates to prepare the 6 cardinal states of the block sphere. After that, we're going to sweep the quantum channel of interest. So in this work, it's going to be the idling channel, this variable time delay between state preparation and measurement. But in general, it could be whichever quantum channel you're hoping to diagnose. And then finally, we're going to apply one of 3 single qubit gates such that we measure in each of the 3 polybases, Z, X, and Y. And once we've collected all our measurement outcomes, we pass it to your favorite classical optimizer to analyze the results and piece together what happened. So if you look at this measurement protocol, you may notice some familiar faces. So we focus on particular combinations of pre and post poles. We see that some subsets of these correspond to classic T1 or T2 measurements. So for example, there's a sequence where we apply a pi pulse, we excite the qubit, we wait some amount of time and measure it in the Z basis, the T1 measurement. We might put it on the equator, wait some amount of time, and measure it in the X basis. That's a T2 Ramsey measurement. Very standard techniques for superconducting qubit experimentalists and quantum computing experimentalists in general. So one way to think about what's going on is that Lindblad tomography is going to piece together all possible combinations of T1 or T2 measurement to tomographically reconstruct the quantum loss channel. So what happens when we actually run this on a real device? So here are the results for running single qubit Lindblad tomography on qubit A, while qubit B is left in its ground state. So here, blue is just corresponding to the raw data that we're measuring in lab, where the x-axis is the idling channel duration, so the amount of time we're waiting between state preparation and measurement, and the y-axis is the probability of measuring the 0 state. And here we get 18 plots corresponding to our 18 combinations of pre and post pulse. Here, the 6 columns correspond to our 6 initial states, the 3 rows corresponding to the 3 measurement bases, where here again I've highlighted a T1 measurement and a standard T2 Ramsey measurement. Okay, so we collect all our measurement outcomes and then we pass it to a classical optimizer for analysis. What's actually going on inside this cartoon computer I've drawn? There are a number of different things we need to do in order to accurately interpret the results of our measurements. I'm going to walk through them step by step. The first is going to be to extract and characterize our state preparation and measurement errors. These are so-called spam errors. And this corresponds to the fact that in real processors, we need to characterize and account for imperfect ground state preparation, so what's going on at the very far left of the circuit, and imperfect qubit state measurement, so here on the very far right. And consistent treatment of spam errors is necessary for interpreting the results of really all tomography, so state tomography, process tomography, and indeed Lindblad tomography as well. So I'm going to go through the math underpinning basically all of this analysis. And the equations are going to start to kind of expand dramatically, but it really comes down to a very, very simple principle of maximum likelihood estimation. So a maximum likelihood estimation, we can write down a function L of the following form. So here, P0 and P1 are going to be the probabilities of measuring either the 0 state or the 1 state when we measure our qubits. And then F and F bar correspond to the number of recorded 0 or 1 measurements. And what makes this expression powerful is that given the measurement outcomes F and F bar, the most likely underlying probabilities can be found by numerically maximizing L with respect to these unknown probabilities P0 and P1. All we're going to do from this is just make a simple substitution. So in quantum mechanics, we know a bit more about the underlying structure of these probabilities. So we can rewrite each of these probabilities as the trace, the density matrix rho times an operator m, so either m0 or m1. Here, rho 0 is just going to be an arbitrary, or rather a general single qubit density matrix, which is going to describe our imperfect ground state. And then M0 and M1 are our measurement operators. So these are the so-called POVMs, the positive operator valued measures, where M0 corresponds to measuring the 0 state, and M1 corresponds to measuring the 1 state. And having made this substitution, the logic is very much the same. Given the measurement outcomes f and f bar, the most likely span can be found by numerically maximizing this function with respect to the unknown matrix elements A, B, or M0, M1, and M2, so the unknown matrix elements of these states and operators. You'll quickly notice that this is a sorely underdetermined problem. We only have 2 outcomes, and we need to measure a whole bunch of unknown matrix elements. Thankfully, we have a whole lot of data to play with. So if we just look at the subset of Lindblad tomography results, where we don't sweep any channel, we just perform state preparation and then measure, we have 18 different combinations of initial state and measurement to play with. So here we can take our maximum likelihood function and add a whole bunch of terms to that product. So here we can multiply over all of our initial states S and all of our measurement axes B, and just append the corresponding term to our maximum likelihood function. So here, rho sub S is just going to be our rotated ground state, and M sub B is going to be the POVM in the polybasis B. The last thing we're going to do is just take a logarithm of this and turn our maximum likelihood function into a log likelihood function. So now we get a sum over all of these initial states and measurement axes. And the final punchline is then that given our measurement outcomes F and F bar for all combinations of initial state and measurement axis, the most likely span can be found by numerically minimizing this function with respect to our unknown matrix elements of the initial state and measurement operators. And one little caveat I'll point out that maybe a careful listener would already have noted is that in general, we would also need to characterize our qubit rotations. So our rotations rho sub S and rho sub B. But in the devices that we're going to be working with, these high fidelity superconducting qubits, these errors are negligible compared to state preparation and measurement errors. And I have more info in backup slides if we'd like to talk about that some more. But this is sort of a characteristic of the era we're living in, where rotations are perfect in some sense in comparison to state thermalization and measurement. So this is a safe assumption to make for the systems we're going to be working with. Okay, so what does all this look like when I'm sitting in lab and trying to measure things? So for example, let's take the example where we're going to put our qubit A into a superposition state and then measure it in the Z basis. So when I do this measurement, this is what it looks like to me in lab. So this is raw data from 1,000 single shot measurements of qubit A. So I'm not going to go into any detail at all about superconducting qubit measurement. Happily point you to this excellent guide. Oh, sorry about that. To this excellent guide that some colleagues wrote recently that goes really into the physics of superconducting qubit measurement. But I will say that superconducting qubit measurement in principle is just recording microwave signals in the IQ plane using a vector network analyzer and then plotting the real and imaginary parts of the signal you get. Once we get these results, we then pass them through a linear support vector machine. It's known as an SVM, and that's going to discriminate these outcomes into either 0 state or 1 state measurements. And then all we need to do is count the number of occurrences on each side of the separator, and this corresponds to the F and F bar that are going to go into our maximum likelihood function. So once we do this analysis, this is the results we get for a single qubit. So here, the skyscraper plots are just showing the magnitude of the different matrix elements for our initial state rho 0 and our measurement operators M0 and M1 where here shaded in are the extracted values of these matrices, and the wireframe corresponds to an ideal state preparation and measurement. This protocol can be really naturally extended to n-qubit systems without a whole lot of added complexity. So here, if we instead wanted to perform 2-qubit Lindblad tomography, all we need to do is prepare now the 36 2-qubit cardinal states. So apply our 6 operations, rho sub s, to each of the qubits and look at all the different combinations. Then we sweep the quantum channel of interest again. And then finally, we measure in all of the 9 different combinations of 2-qubit polybases. So here our spam errors are estimated by minimizing a 2-qubit log likelihood function over all 324 combinations of initial states and measurement axes. And just to quickly show the results of that for this 2-qubit system, here on the top, I'm plotting the results of the initial 2-qubit density matrix. And then on the bottom, the 4 POVMs corresponding to measurement of the 4 computational states in the 2-qubit system. Okay, so that's the spam error characterization at the beginning. Once we've laid that foundation, we can move on to answering an important question. So before we characterize the Lindbladian of the system, we need assurance that the system is Markovian and can be described by a Lindbladian. So next up, we're going to validate the channel Markovianity using Krauss operators. So this is going to entail estimation of the Krauss operators at each discrete channel duration. And then we're going to estimate the channel Markovianity by computing and comparing the evolution of different initial states. So in order to really validate whether or not we get these non-Markovian errors in our system, we need some experimental signature that tells us that non-Markovian errors are occurring. And thankfully, there's kind of a nice signature which allows us to distinguish between each of our 3 types of quantum channels. And it comes when we compare what happens to pairs of states under evolution of each of these channels. So here, let's consider 2-qubit states. So here, the square block and the purple triangle. And we can imagine taking each of these states and evolving it under a common unitary channel. So in this case, just a rotation in the XY plane. And we can clearly see that under a common unitary channel, the trace distance between these 2 states will always stay constant. And this should make a lot of sense because in some sense, a unitary rotation is just a rotation of the Bloch sphere. So we're rotating the Bloch sphere, but the relative distance between points on its surface should always stay the same. In contrast, if we have a Markovian error, we'll find that under a common Markovian channel, the trace distance between pairs of states can only decrease. So for example, to talk about T1 processes again, the state here on the equator will asymptotically approach the 0 state, while the state that's already at 0 stays where it is. So here, the trace distance between these 2 states is decreasing and asymptotically approaching 0. This ends up being a really powerful statement, the statement in the center, because it tells us that if the trace distance between 2 states ever increases under a common channel, the channel has these so-called non-Markovian errors. So one way we can visualize that is, maybe when we have a qubit state on the equator, that's an entangling basis for whatever the interaction with the environment is. So it may appear like this state loses all its phase information as it gets entangled, and then regains it at some later time. So its trace distance relative to some state which never got entangled at all would appear to increase, or rather to decrease and then increase again. So here, the increasing trace distance is our signature of a violation of the master equation. So this was noted, at least as far back as 2009, by Breuer, Lane, and Pilo, when they proposed a non-Markovianity metric based on this principle. So here they propose this measure, which we call, or we term in the paper, in Markov. So this is a maximum over pairs of states, rho 1 and rho 2, where we're going to integrate this function sigma, where sigma is the time derivative of the trace distance between these 2 states. So in other words, we're going to compare pairs of states and we're going to find the two whose trace distance increases the most during evolution under a common channel. So here, n is quantifying the total amount that the trace distance has increased over the course of the evolution of the two states. Or to put it, get to the point and the punchline, larger values of n are going to signify a greater degree of non-Markovianity in our system. Okay, so to estimate, to really get the information we need to do this analysis, we need to estimate the channel at each discrete time. And the way that we're going to do that is to estimate the Krauss operators, which best describe the results of all 18 combinations of pre and post pulses. So here, to return again to our matrix of measurement outcomes of initial state and measurement axis, here in blue again, we're showing just the raw outcome of measurements. And we're going to try to figure out the operators which best describe the results of all 18 measurements. We can do this using another log likelihood function, and I'm not going to go into it in a whole lot of detail, except to say that the structure is very much like the one we used for the span estimation, where now, instead of just looking at the initial state rho sub s, we want to look at rho sub s at some later time ti. So here, rho sub s at time ti is going to be the discrete time evolution of the initial state by some set of Krauss operators, k. And then here, the initial state that we're evolving, rho sub s, and then these measurement operators mb, we already found those during the span estimation. So really all that remains to be found are the Krauss operators. So here, just to summarize it again, given the measurement outcomes at each time step, t sub I, so at f and f bar, the most likely process maps can be found by numerically minimizing this function with respect to the elements of these Krauss operators k. Okay, so here again, I'm showing the outcome of measurements, and to really kind of focus in on maybe some of the most revealing information, let's just look at the single set of pre and post pulses, which corresponds to a T2 Ramsey measurement. So here I'm just magnifying that. Again, we're sweeping on the x-axis the idling channel duration between state preparation and measurement, and on the y-axis we're just plotting the probability of measuring the zero state. And here we're showing that the Krauss operators that we've extracted using this first phase of Markovianity analysis. And we find that we get Krauss operators which very well describe the results of measurement. And once we've obtained these operators, we can now apply this measure that I referred to earlier. So here I'm plotting the trace distance between a pair of states of qubit A as a function of idling channel duration. And here we notice that the trace distance between these two pairs of states, for the large part, decays monotonically. And this is exactly what I was pointing to earlier when I noted that these Markovian errors, when two states evolve under a common Markovian channel, the trace distance between them will monotonically decrease, as we're seeing here, here in the blue data. And the red is just showing the difference in trace distance between adjacent time steps to really highlight whether or not we're seeing an increase or a decrease in the trace distance with time. Okay, so all of this so far has been looking at qubit A when qubit B was just left alone in its ground state. What happens if we change the state of qubit B and repeat all the same measurements and analyses on qubit A? So here we're going to put qubit B into an excited state and repeat this whole story. When we do that for our system, we get, again, another decaying oscillation. That's kind of a hallmark of a Ramsey measurement. But we notice that the frequency of the oscillation has changed quite a bit. And this is perhaps not surprising to us because we know that our two qubits have this always-on ZZ coupling between them, which leads to an increased Ramsey frequency when qubit B is excited. So here, this is just that frequency shift of the 1-1 state corresponding to this coupling. But nonetheless, we can do the Krauss operator extraction again, and we find very good fits to our data, which shouldn't be too surprising to us. If we repeat this and look at this Markovianity metric, we find that again, for combinations of initial states on qubit A, we get this monotonic decrease in the trace distance. And once again, this is consistent with what we're calling these Markovian errors. Okay, what happens now if we put qubit B into a superposition state? And what we get is actually a much more interesting measurement. So here we see that our measurement has a superposition of oscillations. So we see the low frequency oscillation corresponding to when qubit B was in the ground state and the higher frequency oscillation for when it was in the excited state. We see these two oscillations superposed on each other. But if we run this through the same analysis, we can get Krauss operators, which describe the evolution at each discrete time. But now if we take these Krauss operators and we put them through our Markovianity test, we get something very different. So here we don't see a monotonic decrease, and instead we see these very clear periods of increasing trace distance. And this is that signature I was pointing to earlier that really flags that we have a non-Markovian process, where the trace distance between pairs of states on qubit A are, for certain time intervals, getting closer to one another, and then decreasing and getting closer to each other again. And this is consistent with that kind of toy model that I showed earlier in the talk, where we just imagined what would happen if we put qubit A into a superposition state and let it evolve corresponding to an always-on interaction between our two qubits. This, again, is this non-Markovian process I was pointing to earlier. Okay, so again, this shouldn't be too surprising to us, because while I've drawn this kind of simple single qubit circuit at the very top, where we put our qubit onto the equator, we wait some amount of time, and we take it back. In reality, we're just looking at a slice of a two-qubit process. So the qubits are evolving under a multi-qubit channel, and we're only measuring qubit A. So we're losing information about what's happening with qubit B. So the natural question then is, okay, what if we do this exact same thing, but we now look at the outcomes of measurements of both qubit A and qubit B? So here, this would correspond to doing 2-qubit Lindblad tomography. And to do this, we're just going to run this protocol using the results of the 2-qubit spam errors that I showed earlier in the talk to extract the Krauss operators now from all 324 combinations of initial state and measurement axes. So when we do this, this is kind of the raw data that we measure in lab. We're now on the y-axis. I'm plotting the probability of measuring the joint ground state, so the 0-0 state of the two qubits. And while the oscillation has gotten quite a bit more complicated, there's still no problem extracting the corresponding 2-qubit Krauss operators, which describe evolution at each discrete time. And we can take this, put it into our Markovianity metric, and now we see that to a large degree, the trace distance is decreasing monotonically. So now in the 2-qubit picture, it looks like we have a Markovian error again. And this again shouldn't be too surprising, because this is exactly the picture I showed at the very beginning, where now we're monitoring what's happening to both of the qubits. And we see that, over time, the qubits are becoming entangled with each other and then unentangled with each other. So in the most ideal picture, this would be simple unitary evolution. But we know that in our physical systems, we have some Markovian errors as these qubits are exchanging information with their environment. So in net, the process is Markovian, and our Markovianity signature is telling us that as well. Okay, so we extracted the Krauss operators, we extracted our spam errors, we've looked at the degree of Markovianity in the channel. Now we can actually kind of get to the star of the show and estimate the dynamic Hamiltonian and Lindblad operators, which correspond to our qubit evolution. So to do this, we're going to estimate these operators, which describe evolution of this channel for continuous time t. And then we can compare the results of this Lindblad fit to the Markovianity results in a way that should be clear in a couple slides as kind of a complementary check on our Markovianity metric. Okay, so at the very beginning of the talk, I kind of alluded to these T1 and T2 processes, which can be described by a master equation and by a Lindbladian. And so here we have these jump operators and corresponding decay rates. And the idea of Lindblad tomography is going to be to find the Hamiltonian H, the jump operators L, and the corresponding decay rates, which describe the evolution of our qubits for all initial states, all measurement bases, and all time steps t. So to go back to our picture of kind of the aggregate results for a single qubit, we need to find the curves which correspond to every data point that you're seeing on this plot, both T1-like processes and T2-like processes. Again, to do this, we resort to maximum likelihood estimation. So now we need to run the estimation over all of our time steps. So here our likelihood function is now a sum over all of our time steps at t sub I, where the likelihood function at each time t has a form that's basically identical to what I showed earlier for the Krauss operators. Except now our states row at these different times are found by numerically solving the master equation for each guess at the dynamic operators. And this is really all we need to find because, again, the initial state of our system and the measurement operators were already found during our initial span characterization. So to summarize, given the measurement outcomes at all time steps, so F and F bar for all initial states, measurement bases, and time steps, the most likely Lindbladian can be found by numerically minimizing this function with respect to these unknown operators, the Hamiltonian and the jump operators, and their corresponding decay rates. So again, returning to our measurement outcomes, again in blue, this is raw measurement outcomes. And now here I've superposed the results of both the Krauss estimation, these are the orange X's, as well as the most likely Lindbladian describing the evolution. And that's the red curve here. So here, Lindblad tomography has found the most likely Lindbladian, which really describes all combinations of initial state measurement axes for all time steps. So that, again, this was just looking at a single qubit A, one qubit B was left in its ground state. What happens if we play this game again, where we change the state of qubit B and ask what happens? So here, now we can imagine exciting the qubit. And when we actually do excite qubit B in the lab, we get this higher frequency oscillation, which can nonetheless be described very well by a single qubit Lindbladian, the red curve here. But if we look at this plot where qubit B is in a superposition state and we get this more complex oscillation, we find that there is no single qubit Lindbladian which will fit this evolution. And this isn't a failure of our analysis routine or a failure of our optimizer. There's real physics happening here. So here, again, we know that our qubits are not evolving according to single qubit channels. It's a 2-qubit channel that captures interaction with its neighbor. And the fact that we're unable to find a single qubit Lindbladian which fits the data is consistent with our earlier observation of non-Markovianity in this channel, because we know that non-Markovian channels simply cannot be described by jump operators and decay rates. So this failure of the fit is entirely consistent with the non-Markovianity that we observe in this channel. However, if we now go to the 2-qubit picture and we look at this more complex oscillation and we run 2-qubit Lindblad tomography and extract the most likely operators, we find evolution that very beautifully fits the results of this measurement. And here now, this really nice fit to a 2-qubit Lindbladian is consistent with this earlier observation that the non-Markovianity disappears in the 2-qubit picture. So how can we imagine using this sort of technique to diagnose errors in larger processors? So here on the left, I've shown kind of a cartoon schematic of a large superconducting quantum processor, a large array of transmon qubits, where here qubits A and B that we've been studying throughout this work can be thought of as these nearest neighbors in this large lattice. And if we want to diagnose sources of crosstalk, we can imagine running something that looks like this, where we look at qubit A and we characterize its single qubit channel, and we look for channels which cannot be fit to a Lindbladian. And we can do that both in terms of the Lindblad fit or in terms of this non-Markovianity metric. And when we see the signature, we can then hunt around the chip and look for the pair, the matching pair, for which this same channel now becomes well described by Lindbladian. And when this signature now disappears, we now get monatomic decay. And while this might seem kind of onerous to, hunt and peck around the device and look for combinations, pairs of qubits that give the signature, from a complexity standpoint, it's actually quite efficient. So if we assume that this interaction between qubits is entirely two-body, which is an assumption that's fair for a lot of platforms, then we notice that the number of 2-qubit patches will only scale quadratically with the system size n. So here, this process won't explode exponentially and can, in principle, be done efficiently, can be done with quadratic resources. I'm approaching the end of my time, so I'm just going to quickly highlight a few other analyses we did throughout this work that we can point to in the manuscript we have up in the archive right now. So 3 that I think are kind of nice to think about. So one analysis we did was to compare the estimated imperfect single qubit and 2-qubit ground states to thermal states. So while in our stand characterization, we left these as arbitrary density matrix, in superconducting qubits, we know that they should be well described as thermal states of an anharmonic oscillator. So here we can ask, okay, how well is our extracted state described by just a thermal state? So an incoherent mixture of 0 and 1 with some finite probability of measuring it in the 1 state. And we find that our results are very consistent with this description of the ground state as a thermal state. Another analysis we ran was to compare the extracted 2-qubit Lindbladian to, I guess, what I kind of crudely call naive single qubit amplitude damping or dephasing channels. So these are maybe the kind of simplest pictures you'd use to describe single qubit T1 or T2 processes. And then here in this plot, which I won't go into in any great detail, again, we're plotting the idling channel duration on the x-axis, and on the y-axis, we're plotting the diamond norm between our extracted 2-qubit Lindbladian and these so-called naive channels. And we find that there is some disagreement between the two, which is good. We would expect to see some. And this is consistent with the fact that we're well describing relaxation to a thermal state at finite temperature, which this naive amplitude damping and dephasing would not capture. So in some sense, we're capturing the true evolution of our state, which these two pictures would not well describe. And then one final analysis that I'll point to here that I think is kind of nice is to compare the steady state of the extracted 2-qubit Lindbladian to the initial imperfect ground state that we characterize in our span estimation. And we find that the trace distance between the steady state 2-qubit state and the initial state is quite close. And this is reassuring because in superconducting qubit systems, the way we initialize our qubits is just to weight many multiples of T1 and T2 and allow our qubits to relax to the steady state of their channel. So the fact that the steady state, our extracted channel, matches the initial state very nicely corresponds to what we're actually doing in lab to prepare our qubits in the first place. And for further details and for a number of additional analyses we ran, I'd really happily point you to this archive paper that we recently put out that really outlines our technique in a lot more detail. For further directions to take this work, I think going forward, the way we imagine Lindblad tomography is that it's a technique for characterizing really any number of qubit loss channels, which might arise due to a range of physical mechanisms. And for superconducting qubits, where I work, I can think of just 3 off the top of my head that kind of cause experimentalists headaches when thinking about noise in our devices. So, for example, something that we think a lot about is coupling to coherent 2-level systems, so-called TLSs. So here you can think of, instead of having 2 qubits, A and B, coupled to one another and exchanging information, qubit B might be a defect in your material, for instance. So it's coherent two-level system, and your qubit may be exchanging information with it dynamically in time. Another source of error in superconducting qubits is interaction with these non-equilibrium quasi-particles. So we're looking at what happens to uncoupled electrons as they tunnel across Josephson junctions in a superconducting qubit. And then one additional one would be dephasing due to photons in your readout resonators. And here, these are maybe, in the weeds of what superconducting qubit experimentalists worry about. But there's nothing particular about these three that lend themselves well to Lindblad tomography, except that each of these noise mechanisms will contribute to the extracted Lindbladian and result in various degrees of non-Markovian error, which our tomographic routine will help you characterize. And moreover, as I pointed to at the beginning of the talk, since Lindblad tomography is hardware agnostic, if you work in a different system, if you work in trapped ions, if you work in neutral atoms, I'm sure experimentalists in all those fields have their own set of things to worry about. So you can pick your favorite three from your favorite qubit modality. And since Lindblad tomography is hardware agnostic, it will likely be a valuable tool for diagnosing those as well. Okay, so I'm going to quickly summarize and conclude there. So throughout this talk, I've discussed a new qubit characterization protocol we developed, which we call Lindblad tomography, for reconstructing the dynamic loss channels of multi-qubit devices from an ensemble of time domain measurements. So this routine includes characterization of spam errors, validation of channel Markovianity using Krauss operators. And moreover, we took this technique and we demonstrated it on a small superconducting quantum processor, where we extracted the single qubit Lindbladian for a range of qubit configurations, as well as the full 2-qubit channel. We characterized the non-Markovian errors due to these always-on ZZ coupling between transbond qubits. And then we compared these extracted operators to traditional T1 to T2 processes. And as I said in the previous slide, going forward, we think that Lindblad tomography can be used to characterize really a broad range of noise mechanisms in the qubit environment, and will ultimately provide a valuable tool towards these tailored quantum error correction protocols. And for more details, I really encourage you to check out our recent preprint, which is now in the archive, where we outline this technique in a whole lot more detail and talk about a bunch of additional analyses we ran on our system. And with that, I'll conclude the talk, and I'd be happy to open up and open up for questions. Thank you all so much for listening.
Thanks very much, Gabriel. There's a couple of questions in the chat. So the first one's from Siwi. She's asking, in the maximum likelihood estimation step, is it straightforward to do the minimization, or do you have to find yourself, or do you find yourself landing in local minima?
Yeah, it's a great question. And, these optimizations can be, somewhat spooky and mysterious sometimes. Finding yourself a local minimum is definitely a concern. And one way that we try to mitigate that is by varying our starting state. So for example, for our, when we're hunting down for the right jump operators, we can choose a bunch of different starting jump operators. So we can start with, single qubit amplitude damping and dephasing as a first step. And then we can, change it, see if that changes what we converge to. And then ditto for the spam errors. We can change what our initial state and measurement operators are. And so for the results that I presented in this talk, that came from a pretty robust search of, trying out a bunch of initial guesses and then iterating from there, and then showing the results that converged for a range of different guesses. But your intuition is exactly right that, these optimization routines are certainly sensitive, and in these hard searches, falling to a local minimum is definitely something that you need to think about. And we're definitely interested in characterizing this in greater detail and really figuring out reliable metrics for guaranteeing that you're in the global minimum or as close as possible to global.
Thanks. I have a question myself, actually.
Yeah, sure.
So when you do the setup for the state, when you do the state preparation at the start, you do a first set of local rotations. Then you expose it to the natural Hamiltonian of the system for some time. Then you do another set of measurements and another set of rotations, and then you measure. These two rotations, you made the point that they're almost perfect, or at least they're much more perfect than everything else. That is almost certainly true when the neighboring qubit is in 0. But when you've got two qubits going and you're rotating them both, so that one is in a superposition when you're rotating the other, and you know that you've got this ZZ coupling there, meaning that there is no clear one frequency for that qubit. How do you deal with that? Does that not create additional error?
That's a great question. So maybe I'll just hop to a backup slide where I should have acknowledged all my great collaborators at both MIT and Lincoln Lab, as well as my theory colleagues at TU Delft and University of Copenhagen. It's a long talk, so I forgot to flip to the most important slide. But to go to your question, so, backup slides, the way we characterize this is using randomized benchmarking, so specifically interleaved randomized benchmarking, which is really a beautiful complementary technique for this work, because RB is insensitive to spam errors. So in some ways, it's a really good way of validating how good are your gates independent of state preparation and measurement. And so if you need good gates in order to do state preparation and measurement characterization, and this kind of is the missing puzzle piece. The reason we say that these are perfect is that we can look at our fidelities from RB and show that they're orders of magnitude lower than the corresponding errors in measurement, for instance. And so your intuition is exactly right that, we do need to worry about the interaction between your two qubits, though this is captured in our routine. So here we're doing simultaneous RB, where we're doing operations on both of the qubits at the same time and looking at the fidelities. So any interaction between the two would be captured in this number. The reason we still get so high fidelities is that the timescales are very different. So our single qubit rotations are 30 nanoseconds long. And here we're seeing, ZZ coupling on the order of 80 microseconds. So while it's true that during those 30 nanoseconds, you're getting some coupling between your two qubits, it's just a much smaller effect than this long time scale evolution that we can quantify non-recurrently again. But your intuition is great, and certainly when you start characterizing two qubit gates, for instance, this ZZ interaction can become a real player in limiting gate performance. So for trans-1 qubits, there's a lot of really exciting work happening for designing gates that entangle your qubits while suppressing as much as possible this always-on ZZ interaction. So for single qubit gates, not so much of a problem, but definitely something that we think about for two qubit gates.
Okay. Another question from the chat is Lindbladian tomography limited to two-level systems?
That's a fantastic question. It's in its current formulation, yes. It is something that we're actively pursuing. And there are a number of reasons why this is interesting. So, for trans-1 qubits, we often worry about leakage out of the computational subspace. And this comes into play when we do control phase gates between our qubits. And we use these higher levels of the qubits in order to, the ZZ coupling, when our qubits are, tuned into resonance with one another, we use that energy shift in order to, do a control phase shift. But you can get some leakage into the two state, for instance, and their, characterization of the Q-trit state would be super useful. It's kind of an open question in a lot of tomography in general. So state tomography and process tomography are usually only defined in two-level systems as well. And there is some work being done to do tomography of Q-trit states, for instance, and Q-dit states more generally. So I think in principle, there's nothing limiting this technique to 2 qubits. But you'd have to write a corresponding measurement protocol that initializes combinations of ground state, excited state, superposition states of a Q-trit system, right? And there are experimental complexities that go with that, but in principle, I don't see a conceptual bottleneck there.
Okay. Sorry, one more from me, actually. Have you thought about how you would measure this in a large system? So this is with a couple of qubits, but suppose suppose you try to do it on Sycamore or something like that, where there's, kind of 50-ish qubits.
Yeah.
That's a lot of pairs.
Yeah, it's a lot of pairs. I mean, I'll go back to the cartoon I showed over here. It's a lot of pairs, but in a complexity sense, it's not 2 to the 50, right? It's 50 squared.
Sure, but your calibration drifts, right? So you don't have a month to measure it all.
Sure.
So I'm just wondering, are there ways of doing multiple measurements in parallel or anything? Like, are there any ways of getting your result quickly?
Yeah. I'll say that we haven't thought a whole lot about that. I think is the short answer. I think it's definitely something worth pursuing, because if you ultimately, if you're performing this on, you divide your processor in half and do it, in parallel, perhaps then you need to worry about what pairs of qubits across a processor are doing to one another and how that might be changing it. Though for the sort of crosstalk we're talking about, if you say that, you're 100 qubits separated from one another, this crosstalk is likely negligible, at least due to this intrinsic capacitance. So, I'm sure there are a lot of games you could play, and we haven't really explored that in this work. But it's definitely a question that needs to be asked.
Okay, thanks once again for giving us the talk. It was really extremely interesting. And I think a lot of these plots look very familiar, at least to Siwi and I, because we had been looking at something very similar in around 2019. It's different, not the same thing at all. But yeah, this is really definitely very interesting to us. So thanks very much.
Thank you so much for having me. Thank you so much for listening to the talk.